Hello students, and welcome again to Chemistry 101. This is a continuation of chapter 4, and we are just about to finish the concepts of acids and bases. I really here need to discuss the idea of major ions. So as we learned that a strong acid like HCl, for example, when you put HCl gas, which is called hydrogen chloride, you see here in this picture to the left, it's made of molecules of H and Cl connected together, but when you put it in water, this HCl dissociates completely into ions. So it goes into H plus and Cl ions. So there are no more molecules of HCl now. We have all H plus and Cl minus. Or generally speaking, we can say H plus and A minus. And therefore, the major ions in any strong acid, that would be the H plus and the A minus. There will be no HA at all. The story is different when you have a weak acid. In the case of a weak acid, let's say call it HB, before the ionization, before you put it in water, it's made of molecules again of H and B, and they are connected, as you see in the picture to the right in the blue, in molecules. When you put it in water, some of it will dissociate into H plus and B minus, but the fact of the matter is that the weak acid, most of it stays as HB. It does not actually ionize completely, and therefore we say the major ions in a weak base, in a weak acid solution, it's the HB and the H plus and the B minus. So let us practice this in this question. The question says, what are the major species in HBr, HF, aqueous, acetic acid aqueous, and carbonic acid H2CO3? So here we have HBr, which is, as you know, it's a strong acid. So when you put HBr in water, this should dissociate into H plus plus Br minus. You can write this equation as well as HBr plus water liquid. It's forming H3O plus, which is the hydronium ion, plus Br minus. So saying hydronium ion and or H plus is equivalent. In this case, the major species, this is 1 hour reaction, okay? Once HBr is in water, there is no HBr anymore. It converts completely to H plus and Br minus, and therefore the answer for this question, the major species is H plus, I would say H3O plus to be more accurate, and Br minus, and that's it. So there is no HBr in aqueous solution of HBr. For HF, it's a different story. HF is a weak acid. So if you want to put this in water, it will form some H3O plus, okay, plus F minus, but most of the HF will stay as HF, and therefore the major species are HF, H3O plus, and F minus. You can also say HF, H plus, and F minus, and that's also correct. Notice the difference here, that in the case of HBr there is no HBr, but in the case of HF, most of the HF stays as HF in solution. Another example is acetic acid, which is a weak acid. If you put this in water, it's weak, so you have to draw 2 arrows, an H plus the acetate ion, which is CH3COO minus, and therefore you have 3 of them. You have the CH3 COOH as a major species. You have also H plus, and you have also the acetate ion. They are all going to exist in the aqueous solution of this. Carbonic acid is a different story here. Carbonic acid it's a weak acid, and it ionizes 2 steps. The first step, it will form H plus plus HCO3 minus, the hydrogen carbonate. Hydrogen carbonate is an amphoteric species. It acts as an acid in the next step. It will also forming H plus plus CO3 2 minus. But this is a weak acid anyway, so the amount of H plus and the CO3 and the HCO3 minus is little, and that means what the amount of carbonate is much more less than even HCO3. In this case, you only consider the first step in these type of reactions, and therefore the major species are the carbonic acid, okay, and the H plus from the first step, and also the HCO3 minus. you will not find much carbonate in this reaction, because of the fact that HCO3 minus in the second state produce very little amount of carbonate. So these are the major species for this reaction, and by this we have finished the topic of acids and bases. Now we move on to another subject, which is oxidation reduction reactions, and sometimes we call them redox reactions, referring to reduction oxidation, a redox. So we learned that acid-base reactions involve proton transfer. So there is an H plus, a proton, that goes from an acid to a base according to the Bronsted definition. But in oxidation reduction reactions we have an electron transfer, okay? And this is different. An example of that would be sodium metal oxidizing to a sodium ion plus an electron, so that's losing electron, that's oxidation. And a reduction means a chlorine molecule may be taking electrons and forming chloride ions, so that's the reductions. So in oxidation there is always a loss of electrons, or electrons are lost, and in reduction there are electrons are gained, okay, or there is gains of electrons. And so you can remember this by the famous all reg. So oxidation is loss, reduction is gain, okay, all reg. So in the oxidation reduction process there is always an electron or more going from one species to another, okay. The species that losing electrons, it's called we say this is oxidation, and for the species that is gaining the electrons we say this is reductions. Before we go further into the oxidation reduction business, we have to define what is the oxidation number. The oxidation number basically is the charge the atom would have in a molecule or an ion compound if electrons were completely transferred. And to determine the oxidation number of molecules, we have some rules. The first rule says that for free elements in their standard states, the oxidation number is 0. So for example, for sodium, sodium exists in nature as sodium metal. Okay, sodium solid, that's it. So the oxidation number of that would be 0. Not only sodium, but all the metals, potassium, lithium, beryllium, calcium, all the metals, including the transition metals, like iron, for example, or gold, they exist as free atoms in nature, and therefore their oxidation number is 0. For the non-metals, they exist as diatomic molecules, like oxygen exists in nature as O2, and there's also N2 and H2 and Cl2, all the halogens, F2, Br2. These people, they have also oxidation number of 0 if they exist by themselves in a chemical reaction. For phosphorus it's P4, and for sulfur it's S8. For carbon it's actually C graphite. Now the other rules we know them anyway, because we know that the group 1 they take +1, therefore the oxidation number is +1. So you have lithium plus, that means the lithium, the oxidation number is +1. For the transition metals, like for example, if E3 is 3+, so the oxidation number would be 3+, and so on. Oxygen usually takes -2, except few cases where it takes -1, such as in the case of hydrogen peroxide. Oxygen in that case is -1, but generally speaking, oxygen is -2. And the oxidation number of hydrogen is +1, except it's in the hydride. And in that case it's -1. I'm going to explain this in a minute. And also the sum of the oxidation number of all atoms in a molecule or an ion is equal to the charge in the molecule or ion. So that's important, that the sum of the oxidation numbers in a molecule should equal to the total charge. Finally, oxidation numbers do not have to be integers, so they don't have to be whole numbers. They might be fractions, and this is an important rule. For example, the superoxide O2 minus, it has an oxidation number of -0.5. Now this is a table that shows you possible oxidation numbers. So here we have group 1, they always +1, group 2 is +2. Carbon usually does +or -4. It could do +2. Now for the halogens, we learned that they are usually -1, but you will see here that chloride, for example, the chlorine atom, it could do much more than 1 oxidation number, as we're going to see in a few seconds. So to put this into practice, we have a question here. We have an example that says, what is the oxidation number of nitrogen in nitric acid? So we're asking about the oxidation number of this guy. Now we know oxygen is -2, and hydrogen is +1. So we can do the mathematics by writing an equation that 1 plus n plus 3 times minus 2 is equal to 0, which is the total charge in HNO3. HNO3 is in neutral, there is no charge, so that should all equal to 0. Then that would be 1 plus nitrogen minus 6 equal to 0. And if you do the math, you will find that nitrogen is plus 5. So the oxidation number of nitrogen in nitric acid is plus 5. Another example would be HCl04. I know that oxygen is always minus 2, and this is plus 1. I'm asking about the chlorine. Chlorine might be, well, chlorine usually minus 1, but in this case it might be different. So I'm sure about the oxygen, I'm sure about the hydrogen, I'm not sure about the chlorine, because as you saw in the previous table, chlorine that might take more than one oxidation number. So you can do the same thing here, 1 plus chlorine plus 4 oxygens times minus 2 is equal again to 0, because the original molecule, the HCl04 perchloric acid, is 0. In this case, 1 plus Cl minus 8 is equal to 0. You can transfer the 8 to the other side, it would be 8, and you will find here that Cl actually has an oxidation number of plus 7. Okay, so notice here that I'm writing the oxidation number in terms of the charge first and the number after, so plus 7, plus 8, plus 2. And before we were writing the ion as 2 plus or 3 plus. So the number first and then the charge. And this is how you differentiate between the charge and the oxidation number. So for a species like magnesium ion, Mg2 plus, I say that Mg2 plus, this is the ion charge, okay? But the oxidation number of Mg is equal to plus 2. Okay, so oxidation number is plus 2, but the charge is 2 plus. Another example here, assign oxidation number for all the elements in the following compounds and ions. So we have Li2O, nitric acid, I have already did a nitric acid, and Cr2O7 minus, 2 minus. So we have here Li2O, I'm sure that, well, oxygen is always minus 2, so lithium is plus 1. So you see here, plus 1 times 2 is plus 2, and then minus 2, they add up to 0, which is the total charge in lithium oxide. That's an easy example. We have did this already, and we just find this to be plus 5. For the case of the dichromate, I know that oxygen is minus 2, chromium is unknown. The total charge on the ion is minus 2. So this minus 2 is the charge on the total ion, and therefore I can say that 2Cr plus the oxygens, which is 7 times minus 2, is equal to minus 2. So this minus 2 is the ion charge, the original ion charge that was in the question. In this case, we say 2Cr minus 14 is equal to minus 2, and therefore 2Cr is equal to 12, and that will give you Cr is equal plus 6. So you see here, chromium is making an oxidation number of plus 6, which is okay for a transition element. I told you about hydrogen. Hydrogen always, most of the cases, like so for example in HCl, Cl is minus 1, hydrogen is plus 1. So hydrogen takes plus 1 unless it's an anhydride. Anhydride is an hydrogen connected to a metal. For example, in sodium hydride, so NaH, this is called sodium hydride. In sodium hydride, there is no way that sodium takes a minus. It's always plus 1, and therefore the hydrogen must take the minus 1. And this is a case where hydrogen takes a minus 1 oxidation number in hydrides. Okay, so keep this in mind when we do questions. Now we move on to the oxidation reduction reactions, as we learned about oxidation numbers. Now we need to apply this into redox reactions. Oxidation reduction reactions or redox reactions, they are represented 2 steps. There is oxidation step and there's a reduction step. Let's take an example of sodium and chlorine. You know, sodium can form sodium ion plus electron, and this is called oxidation because it is loss of electrons. This electron can go to chlorine, So this is 1 electron, and that will form Cl minus, and this is called reduction. Sodium can exist in nature as sodium metal, but the chlorine in nature does not exist as Cl atom, it exists as Cl2, and therefore it needs 2 electrons, and that will form you 2 Cl minus. If you combine these two reactions into one step, you get Na plus Cl2 goes to 2 NaCl. This is an example of an oxidation reduction reaction. Now let's take a look at the oxidation number in these reactions. I told you that for free atoms, like sodium by itself, the oxidation number is 0. And Cl2 gas has also 0 oxidation number because it's an element in its standard state. An element in its standard states means the state of the element, like whether it's solid, gas, or liquid, at room temperature and ambient pressure. So chlorine gas is a gas at room temperature, and it exists as a diatomic molecule as in Cl2. Now we have a compound NaCl, so the oxidation numbers of course are not 0. You have to assign the oxidation numbers, and for sodium it's +1, and for the chlorine it's -1. Now you see here that sodium is going from 0 to +1. This is called oxidation because it is increase in the oxidation number, and this is another definition of oxidation. Oxidation means losing of electrons or the increase in the oxidation number. But for chlorine, it's going from 0 to -1, so the number is decreasing, and this is called reduction. So here we say, if you have an increase in the oxidation number, this is called oxidation, and if you have a reduction in the oxidation number, this is called reduction. Na is oxidizing in this equation, and therefore it's called the reducing agent. Chlorine is reducing, it's going from 0 to -1, so there is a reduction happening. This is called the oxidizing agent. And why is that? Because sodium is oxidizing, that means somebody has oxidized it, and that means, which is the chlorine. Chlorine is reducing, there is somebody who reduced it, which is the sodium, and that's why we call the sodium reducing agent. It's called reducing agent and oxidizing agent, not oxidation agent or reduction agent. Okay, just keep this in mind. Another common example here is the combustion of methane in the presence of oxygen to form CO2 and H2O. This is also an example of oxidation reduction reactions. The equation is not balanced, but that will not actually affect your consideration of an oxidation reduction. I can balance it. This is 2 here, 2 there. This is gas in its standard state. This is also gas, this is also gas, and this is liquid. Now oxygen has an oxidation number of 0 because it's an element in its free state. All the others are compounds, so we have to assign their oxidation number. I know H is +1, it's not a hydride, so it's +1. +1 times 4 is +4, that means this is -4. And here oxygen is -2, so -2 times 2 is -4. This means carbon here is +4. You see carbon is changing oxidation numbers. This is -2 and this is +1 because it's a compound, therefore we assign the oxidation numbers as such. So clearly here we have carbon that is going from -4 to +4, so that there is an increase in the oxidation number, and this is called oxidation. And therefore this is the reducing agent. If there is oxidation, there must be a reduction, and if you look at the equation, the O2 goes from 0 in the reactants into -2. The oxidation number is reducing, that means this is reduction. Okay? And therefore this is the oxidizing agent. So, and this is where the term oxidation came from, because this is the reaction with oxygen. Oxygen is oxidizing the methane, and this is where the historical definition of oxidation came from. It's reaction with oxygen, where oxygen acts as an oxidizing agent. But now many redox reactions takes place without oxygen. So that means we have reactions that involve oxidation reduction, but that does not involve oxygen in their reactions. So this is another example of Mg, magnesium, reacting with oxygen to form magnesium oxide. And if you want to break this down into 2 equations, the first one will be 2Mg will go to 2Mg2 plus 4 electrons, and for those 4 electrons will go to oxygen to reduce it to 2 minus, okay? This is called half reaction, half oxidation reaction and half reduction reactions. When you add these two reactions together, you will obtain the redox reactions. Here is another example of zinc reacting with copper sulfate to form zinc sulfate and copper. This is called this displacement reaction, as we're going to learn soon. And this is a type of oxidation reduction reaction. If you assign oxidation number, it's easy for you to understand why it's a redox reaction. Zinc solid is a zinc by itself, it's an element, so it has an oxidation number of 0. The copper sulfate, the sulfate has 2 minus, so you can just keep it as 2 minus, therefore the Cu is 2 plus. And zinc sulfate, the Zn now is 2 plus and the sulfate is 2 minus, and copper at the end has 0. So you see here that the zinc is oxidizing and the copper is reducing, so you can easily write down the the two half reactions, the oxidation reaction and the reduction reactions, okay? And here we can say that the zinc is the reducing agent and the copper is the oxidizing agent. This reaction is another one. For the following reaction, iron oxide reacts with carbon monoxide to form iron metal plus carbon dioxide. This reaction is used in the industry to produce iron, which is a very important commercial element, out of iron oxide, which is a cheap ore of iron. Here we say we need to write the half reactions, oxidation reduction, indicate which element is oxidized and which one is reduced, and also indicate which one is the oxidizing agent and which one is the reducing agent. So here is our reaction. We have FeO solid and we have CO gas, and this is Fe solid and this is CO2 gas. One of them is 0, which is the iron. The iron metal is a metal by itself. It's an element by itself, so it has an oxidation number of 0. We did this before. This is -2. -2 times 2 is -4. That means carbon is +4. This is -2 there, and that means Fe is +2. For CO, it's -2, and carbon is +2. So you see here, Fe is clearly reducing. Not always metals are oxidizing. Now it's reducing from Fe2 plus to Fe0. So this is your reduction, and that means this is the oxidizing agent. Okay. The carbon, oxygen. There is nothing happening with oxygen across the equation. Oxygen is taking a -2, so that means oxygen is not playing a role here. But carbon is going from carbon. You can do that in a different color if you like. So carbon is going from 2 plus to 4 plus. This is your oxidation. Okay, so we say here that carbon is oxidizing and therefore it is the reducing agent. So to write these equations, you can take the oxygen from the equation. You can say Fe2 plus is going to Fe0, Fe0 solid, and this is reduction. That means it's taking electrons, and how many electrons we need to do that? We need 2 electrons to have the charges equal. So this is the half reaction for the reduction equation, and for the oxidation reaction, we can just write CO is going to CO2, right? But the oxidation number of C here is +2 and there is +4. That means it is CO going to CO2 plus those 2 electrons that they are forming in the reduction. Okay, so these are your 2 equations for this example. When we talk about types of redox reactions, there are actually 5 of them. There's something called combination, and there is also decomposition. There's combustion. Everybody knows what combustion is. It's basically a reaction with oxygen, and we took many examples on that. We have a displacement reaction, and we have also disproportionation reaction. In a combination reaction, there's 2 things that they're combining to form one product. So there's like A plus B goes to C. The decomposition is the reverse of that. So we have C that is going to A plus B. Okay? So in combination reaction, for example, aluminum can combine with bromine gas to form aluminum bromide. So this is an example of combination reaction. 2Al plus 3Br2 goes to 2AlBr3. So 1 element, 2 elements in the reactants, and one product. This is a type of oxidation reduction reaction, because aluminum is an element and it's a free element. It's not combining with anything. It's not in a compound. therefore it has oxidation number of 0, and the same for bromine, but that's not the same for AlBr3. AlBr3 is a compound, so you need to assign the actual oxidation numbers. In this case, Br has a -1, so -1 times 3 is -3, and therefore aluminum is a +3, and they all add up to 0. So here you can easily say which one is oxidizing and which one is reducing. I will leave this to you to think about. In the composition reaction, this is the reverse of combination. You get C breaking down into A and B. An example of that is potassium chlorate. If you take a solid potassium chlorate in the lab and you just heat it up, that will form you KCl plus oxygen. It will break down in its elements, okay? This is also a redox reaction. So you see here that the composition is a reverse of the combination reaction. The other type of reactions is combustion, where an element is reacting with oxygen. An example is sulfur reacting with oxygen to form SO2, or maybe carbon graphite burning with oxygen to form CO2, and so on. Or a magnesium reacting with oxygen to form magnesium oxide, and so on. You might think that the combustion is, some people they might confuse between combustion and combination. Well, because combustion actually looks like combination anyway. So if the reaction involves oxygen, you call this combustion, okay? But if it's a combination reaction without having oxygen involved, in that case it's only combination reaction. All of these are redox reactions, and I will leave you to figure out which one is the oxidizing agent and which one is the reducing agents in these examples. A displacement reaction is actually the one that is really interested in, because in displacement reaction there is an element that is displacing another element. For example, you have A plus BC going to AC plus B. In this case, A is kicking out B, okay, and hooking up with C. An example of that would be strontium reacting with water. Strontium is a reactive metal. It's in group 2, and these elements in group 1 and 2, they are very reactive, okay? So what happens here is that strontium kicks out hydrogen away from water and replacing it, okay? So that will form a strontium hydroxide plus hydrogen. This is called hydrogen displacement. There is another type of displacement where our metals displacing other metals. Like take for example titanium tetrachloride and magnesium. Magnesium will associate with the chlorine to form MgCl2, kicking the titanium away, okay? So this is a metal displacement. And there is also halogen displacement. Take for example Cl2 plus 2kBr forming 2kCl plus Br2. In this case the Cl2 is kicking the Br away because it's more reactive than bromine, as we're going to learn now. Chlorine is more reactive than bromine, so it will hook up with potassium, the metal, and leaving Br2 by itself. So the question is why this is happening, why some metals are displacing other metals, or some halogens displacing. That's because of something called the activity series. The activity series for metals, it's right here shown to you. At the top of the list here we have all the reactive metals like lithium, potassium, sodium, and barium and calcium. These are very reactive. They can even react with water to produce H2 gas. That's why they're famous. If you take a look at YouTube and just Google sodium with water, you see the explosion happening between sodium and water. Because sodium is very reactive, it will kick water, it will displace the hydrogen in water, forming sodium hydroxide plus H2 gas. And of course the reaction will produce heat, and you will have enough energy to burn the hydrogen, causing an explosion. That's in the green at the top. This is followed by some elements. They are reactive, but they are kind of less reactive than the first, like magnesium, aluminum, iron. These people will react with hot water or steam to produce hydrogen. So they can displace hydrogen, but at vigorous conditions. This is followed by cobalt, nickel, lead, and tin. They can react only with acids to produce hydrogen. Okay, so they need more hard conditions. And then you have hydrogen, which is the yellow line. So anything above hydrogen it is reactive, it can replace hydrogen and water, but anything below that, it won't do that. So copper, silver, gold, platinum, these are unreactive elements. That's why they are precious, that's why they are expensive, because they cannot react with water. These people, they do not react with water or acids to produce H2. That's why gold is expensive. It does not, react with water or an acid or anything. So applying these rules here, if you take calcium, for example, calcium is a reactive metal and it's at the top of the yellow line. If you see the yellow line for hydrogen, calcium is above that. So calcium can react with water to form Ca, calcium hydroxide plus H2 gas, but that does not happen to silver. Silver, for example, it can't do that. Silver is less reactive than hydrogen, and therefore it won't displace hydrogen in water. So this reaction does not happen. For halogens, they follow the series that F2 is more reactive than Cl2, is more reactive than Br2, is more reactive than I2. Therefore, I2 is the least reactive of these. Okay, F2 is crazy reactive. So for that, now you understand why Cl2 plus Kbr goes to KCl plus Br2, because chlorine is more reactive than bromine. It will hook up with potassium, kicking Br2 away, but the reverse does not happen. Br2 plus 2KCl does not produce UKBr plus Cl2. The reverse of this reaction is not possible. And now we understand why a reaction like this does not only happen. I2 plus 2KBr goes to 2Ki plus Br2. This does not happen because I2 is less reactive than bromine, so bromine will still associate with potassium, and this reaction won't happen. But the reverse of this reaction will happen, by the way. If you react in some bromine with potassium iodide, it will form Kbr plus I2. The next type of reaction is called disproportionation reaction. In this proportion reaction, an element in one oxidation state is simultaneously oxidized and reduced. This is a very interesting example here, where you have chlorine plus OH minus going to ClO minus plus Cl minus plus H2O. In this case, chlorine has 0 oxidation number because it's an element in its free state. And you have O, and you have here ClO minus. You can do the math and find out that the oxidation number is +1. Cl minus, the oxidation number of chlorine in Cl minus is -1, and you have the water. So chlorine is reducing and oxidizing at the same time. And basically it's actually it's the reducing agent and the oxidizing agent. It's the Ra and OA at the same time, and this is called a disproportionation reaction. Okay? This happens in many cases, and it's very interesting to see these cases. Based on that, we can classify the following redox reactions and indicate changes in the oxidation number of the element. We have 4 examples that we are going to discuss in the class, inshallah. So that would be the end of this lecture. In the next lecture, we are going to continue with the concentration of solutions and discuss more on the concepts of molarity and molarity calculations. By this, I thank you for listening to my lecture, and thank you so much for listening, and have a great day.